Okay, our problems today center on integration involving the natural log function. We're going to do 3 problems in a row. Here's our first problem, the integral from 0 to 2 of x squared plus 2 over x plus 1 dx. In looking at this and considering some form of u substitution, if u were to be the x plus 1, the x squared plus 2 in the numerator clearly is not a derivative of that. And we run into an issue in trying to make the numerator a u because you can't have your du in the denominator. So I think the best option here is to do long division, and I'll review a little bit of long division over here. So we have x squared, we need the 0x placeholder. X divides into x squared x times, and we end up with x squared plus x. When we subtract, that's 0, negative x, bring down the 2, negative 1 times x plus 1, negative x minus 1, subtract, and we end up with a remainder of 3. So that means our integrand can be simplified to the quotient x minus 1 plus the remainder over the divisor. So our new integral would be the integral from 0 to 2 of x minus 1 plus 3 over x plus 1 dx. And because I know I'm going to do some u substitution here, I'm actually going to split this 0 to 2 of x dx minus the integral from 0 to 2 of 1 dx plus, and the 3 scalar I'll move in front, 0 to 2 of dx over x plus 1. So here we end up with 1/2 x squared from 0 to 2 using our power rule, minus here x from 0 to 2. And then here we're going to do a u substitution where u is x plus 1, du is dx. So we end up with a 1 over u du. And I'm going to complete the change of variable by finding u of 0, plugging in 0 for x, we get 1. U of 2 is 3. So plus 3 times the integral now from 1 to 3 of du over u. So I no longer have to substitute back in the x plus 1 after finding the antiderivative. So we end up with 1/2 2 squared minus 0 minus, I didn't distribute that 1/2 here. Sorry, don't need that there, my apologies. Minus, here we end up with 2 minus 0. Plus 3, here the antiderivative of du over u, natural log of the absolute value of u, from 1 to 3. So 2 squared is 4, 1/2 of 4 is 2, minus 2, plus 3 times the natural log of the absolute value of 3, minus the natural log of the absolute value of 1. 2 minus 2 is 0. The natural log of 1 is also 0, so we end up with 3 times the natural log of 3, which, using our power rule, the natural log of 27, 3 cubed. So there is our first problem. Let's see, let's look at another one. And so now let's look at one that looks a little more complicated than it is. 2 times the natural log of x plus 1 over x times the quantity natural log of x squared plus the natural log of x dx. So clearly it looks a little bit complicated, but I think you'll see pretty quickly that, and again, our focus here should really be on the denominator, with hopefully du or something close to that in our numerator. So if I let u be the denominator, at least this portion, the natural log of x, that whole quantity squared, plus the natural log of x, notice du would be 2 times the natural log of x times, using our chain rule, 1 over x, plus the derivative of the natural log of x, 1 over x, and then dx. Again, notice we have a 1 over x in both terms, so I'm going to factor that out. and we have 2 times the natural log of x plus 1. And just rewriting this slightly, 2 times the natural log of x plus 1 over x dx, which if you look back here, it really is exactly what we have in our integram. So all of this that looks a little more complicated than it is simplifies to 1 over u du. And then our antiderivative, the natural log of the absolute value of u plus c, and we'll plug back in our u, and we know the natural log of the absolute value of the natural log of x, that quantity squared, plus the natural log of x, closing our absolute value, plus c. So looks can be a little deceiving there. Last one, and I really like this one because it actually requires a couple of steps here. We're going to do the integral of the tangent of the natural log of x divided by x dx. And again, we have a composite function here with the tangent of the natural log, and notice an x in the denominator. So I'm going to let u be the natural log of x. Du is 1 over x dx. So we have a nice substitution here, and there is our du. And so we end up with the tangent of u du. Now, you may or may not remember the tangent, but we do get this really by splitting tangent into sine and cosine and doing u substitution. So now I'm going to write this as the sine of u divided by the cosine of u du. And we're going to do a v substitution. So I'm going to let v be the cosine of u. dv is minus sine u du. Our integrand is a positive, so we have a minus dv equals sine u du. So now we have negative 1 over v dv. Sine u du is negative dv, and then the cosine is the 1 over v. Okay, so the antiderivative of the 1 over v is natural log of the absolute value of v plus c. Okay, so now we're going to have to actually back substitute twice. V is the cosine of u. And to clean this up a little bit, I'm going to use a power rule again. So this is the natural log of the cosine of u to the negative 1 plus c, right? That's a minus 1, so applying our power rule. And this negative tells you it's the reciprocal, right? So the cosine of u to the negative 1 means 1 over the cosine of u, which is the secant of u. And some of you may recall that the antiderivative of tangent is the natural log of the absolute value of the secant of u. And now one more back substitution. We'll go back up to what u equals, and we'll plug that into here. And we end up with the natural log of the secant of the natural log of x, closing our parentheses, and our absolute value plus c. So nice little problem there where we're doing a u substitution and then a v substitution.